When you type a question into an AI and hit enter, the response feels instantaneous. A glowing cursor streams back a perfectly reasoned answer, reacting to your specific thoughts in real time. It is an incredibly convincing illusion. As that text flows onto the screen, it is easy to imagine a digital brain mulling over your words and deciding how to respond. However, the system operates on a different set of rules. It handles numbers rather than definitions, and processes statistical patterns instead of conscious knowledge. To see why an AI can write complex software code 1 minute and fail at basic arithmetic the next, we have to pause time. We need to freeze the exact millisecond you hit send and look at the mathematical reality running underneath. The moment your prompt leaves your computer, the model discards the words. Large language models perceive sequences of numbers rather than letters or sentences. This happens through tokenization. The system breaks human words into smaller chunks. Hamburger might be sliced into ham, burr, and gur, each with a unique numerical ID. Linguistic meaning is replaced by mathematical position, snapping into a grid of integers the machine calculates. Understanding tokenization is the first step towards seeing the machine for what it is. Once the text is converted to numbers, the system begins to function as a probability calculator. Those newly created numerical tokens move into the model's working memory, known as the context window. This workspace holds every piece of data required for the response: your initial prompt, hidden system instructions, and the current conversation history. Developers often highlight their maximum context window, claiming their models can hold millions of tokens in this space at once. But filling this workspace has a cost. As token count rises, the model's attention degrades, often ignoring crucial information in the middle. This creates a smaller limit called the maximum effective context window, the actual data the model can process before accuracy breaks down. When an AI ignores a specific fact in a long document, it is often because it has run out of room for that calculation. Holistic comprehension has been traded for a crowded workspace. From the context window, the tokens enter the core architecture. They move through a massive web of mathematical parameters called weights and biases. This diagram shows a transformer architecture. In these attention layers, the model evaluates how every single token in the sequence relates to every other token. These parameters were established during pre-training. By absorbing trillions of tokens from the internet, the model learned the statistical and structural patterns of human language. A model relying purely on raw statistics can be unpredictable. It might generate text that is mathematically probable, but unhelpful, toxic, or unsafe. To steer this behavior, researchers use reinforcement learning from human feedback. Human labelers rank thousands of AI outputs to train a secondary reward system. This reward model optimizes the AI to prefer specific corridors of behavior, favoring safe and helpful responses over statistically chaotic ones. The perceived intelligence of the response is a product of these statistical weights, guided by human feedback into a predictable, useful range. Once the tokens have passed through these attention layers, the model has one objective: calculate the probability of the very next token. It outputs that single token, feeds it back into the context window, and starts the entire looping calculation over again to guess the next one. The system has no vision of the final sentence it is writing. It is simply predicting the next most likely chunk of text in a mathematical vacuum. Let's unfreeze time and return to the interface as the paragraph finishes generating. This entire response was constructed one microscopic probabilistic step at a time. The result is a high-speed, high-dimensional version of autocomplete. Hallucinations lose their mystery when viewed as a calculation error. Sometimes the probability of a false word rises too high, or a crowded context window obscures the truth. Understanding these constraints, the tokens, the context limits, and the statistical parameters, allows us to stop treating these models as oracles. Instead, we can pilot them as the powerful statistical